Yeah, but don't you want to record it on the cloud?
If we record it on the cloud, then if you were to send me the link, because if it's recorded on the cloud, it will be saved under your account. And then if you send me that link, I can't download the video from there.
Yeah, I could just forward the email that I get.
Okay, yeah, if you can do that, if I'm given the option to download the video, that should work just as well.
Okay, yeah, you prefer that?
Yeah, that's totally fine. As long as I can download the video, it's perfectly fine.
Okay. All right, so let's get started. So my goal is to talk about graphs today. And what we want to do, so graphs is it's a big topic, and some of it you probably already know, but a lot of it I may end up teaching you very differently. So you might see some of the old material, but presented very differently, I think. So let's see how this goes. All right. Everyone can see the slides? You're good?
For me, it's a little bit messed up.
There's like a white screen in like half of the screen.
Aha, that's odd. Okay, let's let me see what's going on. How about now?
We see your current slide and the next slide.
Ah, okay. So I have to change this. Swap displays. Okay. Hopefully you're good now.
Yeah, perfect.
Okay. All right. Super. So let me start with some basics. You've all heard of graphs, I hope. A graph really is a mathematical object, and it's the notation typically that'll be used in the textbooks is that it's made up of two sets. One is a set of vertices, and the other is a set of edges that are defined on the vertices, or really on pairs of vertices. So the letter V corresponds to a set of vertices, and the set E is the set of edges that links pairs of vertices. So this you're already familiar with, hopefully. Now, edges can be either directed or undirected. If it's a directed edge, then you write it in a slightly different form than if it's an undirected edge. But the notation will become clear when you see some. Edges can be weighted or unweighted. And there are a few more definitions that we will use. In particular, we'll also store some extra information along with every edge. For instance, this will help us to solve specific problems that may be related to distances, that may be related to various questions we want to ask about shortest paths, about flow capacities, etc., etc. So depending on the kind of information that you attach to an edge, you can then solve very different kinds of problems in the process. Then again, these are terms that you probably have heard before, so I'm just going to go over them quickly. A path is a sequence of edges, and the sequence of edges have to be such that the consecutive edges must share a vertex. So you go from one vertex to the next, to the next, to the next, and that gives you a path. So you can either write it as a sequence of vertices or as a sequence of edges. And a cycle is a special kind of path where the start point is the same as the end point. Then we're also going to define something called a subgraph. A subgraph is essentially any piece of the original graph. So a subgraph of a graph is where you simply take some subset of the vertices and some subset of the edges. Now, this is a very general definition of a subgraph, but then you can also define something called an induced subgraph, which is slightly different. And we'll talk about that later when there is a need for it. And we're going to also refer to some special kinds of graphs. One of them is what's called as a tree. A tree is a graph that does not have cycles. In particular, when we talk about just a plain old tree, we're talking about undirected graphs. So a tree in an undirected graph, a tree is an undirected graph that has no cycles. And a spanning tree is a special kind of tree. It's a kind of tree that touches every vertex. So it connects every vertex to every other vertex. That's a spanning tree. Are any of these definitions strange for you? Do you want me to go over them a little bit more, or are these all pretty clear to you?
Can you go over the spanning tree one again?
Okay, spanning tree, we'll look at some examples and it'll start to make sense. So if that's the only thing that you don't understand, you're in pretty good shape.
Okay.
All other definitions are good?
Yeah, all the other ones are good.
Okay. Anybody else?
Can we say that a spanning tree is a special subgraph?
So remember, a tree is a subgraph where it contains a bunch of edges, but no cycles.
Mm-hmm.
Okay, and a spanning tree needs to span everything. It has to touch all the vertices. That's a spanning tree.
Okay.
Okay. So that's the only difference. So a tree can be, just four vertices and connected by a subgraph without a cycle. But a spanning tree must include all the vertices in the graph. And then, you've probably heard of minimum spanning trees, where you want spanning trees of minimum weight and so on and so forth. Are we good with this?
Yeah.
Okay. All right. Give me just a second. Yeah. So we're going to talk about this. I need to go back here. Yeah. So here are some examples of what are called as graph representations. So what you see up on top here is an example of an undirected graph. There are 5 vertices numbered 1 through 3, 4, 5. And you have something like, what is it, 7 edges here. Now, in order to represent this graph, there are 2 ways to represent them. One is called an adjacency list, and the other is called an adjacency matrix. Adjacency matrices are really quite simple. They have n rows and n columns, where n is the number of vertices. So in this case, since there are 5 vertices, you're going to have 5 rows and 5 columns. And the entries of the matrix are either zeros or ones. You'll have a 1 if, so for instance, over here, vertex 2 is connected to vertex 1. As you see over here, vertex 2 is connected to vertex 1. And so therefore, this entry is going to be a 1. Vertex 3 is not connected to vertex 1. So vertex 3 is not connected to vertex 1. And so therefore, you're going to see a 0 here. So you look at the row and the column, and you look at the entry there. It tells you whether those 2 vertices are connected or not. And the matrix is symmetric in the sense that rows and columns are interchangeable. Is that clear? Everyone okay with this? So that's called a adjacency matrix. So it tells you all about the adjacencies in the graph, and it indicates them as zeros or ones in a matrix. Then you have something called an adjacency list, which is this guy here. In an adjacency list, you have one list for each vertex. Because there are 5 vertices, you're going to have 5 lists. And you get a linked list for each of the vertices that tells you the list of vertices that this guy is adjacent to. So vertex number 1 is adjacent to 2 and 5. Vertex number 2 is adjacent to 1, 5, 3, and 4. So vertex number 2 is adjacent to 1, 5, 3, and 4. and so on and so forth. So that's called an adjacency list. You can do similar things with directed graphs. This here is an example of a directed graph where every edge has a direction. So this particular edge goes from 1 to 2. This particular edge goes from 4 to 2. This one goes from 3 to 5. This one goes from 6 to 6 itself. So this is an example of a directed graph. Directed graphs can also be represented using a adjacency matrix or an adjacency list. Now, these representations are important because you need to be clear about them in order to be able to design efficient algorithms that manipulate these graphs. Okay, any questions so far?
Would there be any adjacency matrix that would have like a 2, or would it just be 1s or 0s?
There are other kinds of adjacency matrices. We'll talk about them when we get there. Here, we are only dealing with, at least in these two examples, we are only dealing with unweighted graphs. If there are edge weights, then you have to figure a way of representing the weights. And one way to do this would be, instead of 0s and 1s, to actually put the weight of that edge. So if the weight of the edge from 2 to 1 is 17, then this entry would say 17, and so on and so forth. So yeah, there are places, ultimately a graph is just a model. It models various situations. If this particular graph here corresponds to a road network, then each of these edges would correspond to a road from city 1 to city 2, city 2 to city 3, or city 2 to city 5. And there are distances associated with it. If there are distances associated with it, then you may want to put that information in your adjacency matrix. So then you would go and change those entries accordingly. So depending on your application, you choose your representation appropriately so that you can answer and solve interesting problems on these specific graphs. Now, with all these graphs, one could ask lots of interesting questions that says, okay, is there a way to get from vertex 1 to vertex 4? Or is there a way to get from vertex 1 to vertex 6 over in this graph? Things of that sort. So you can ask lots of interesting questions. In order to answer those questions, you have to use a representation. And at that point, you have to decide whether you want to use this kind of representation or this kind of representation. Does that make sense? Okay. So this is basic stuff. Hopefully you guys have seen it in your data structures class or in some other class. And the interesting stuff comes after this, where we want to solve interesting problems based on these graphs. Now, the first interesting problem that we're going to solve is what is called as a graph traversal. In a graph traversal, our goal is as follows. Our goal is to visit every vertex and every edge in the graph. Now, there are simple ways to do it, but there are also systematic ways of doing it that will somehow become much more useful when you start to address or solve different problems on graphs. So that's the reason why it's important to understand graph traversals. Now, most of you have probably seen examples of graph traversals. We know that it has to be systematic so that no vertex or no edge is missed. But there are different ways of doing this, and they have very different properties, which helps us to solve very different kinds of problems. Now, the most popular kind of graph traversal that you probably have seen is what is called as, anyone know what this is?
Depth first search.
Depth first search, thank you. So depth first search is the standard graph traversal that most students look at, are taught in one of their classes. So you've probably seen that in either programming 2 or graph or your data structures class or your algorithms class. And our goal is to see if we can understand this properly. Now, most of you know depth first search. You can probably even describe it to me in simple terms. But today, you're going to learn this in a very different way. So let's pay some attention and see if we can understand this in the way that I want to explain this. Are there any questions? Okay, if there are no questions, let's get to this example. So here's an example of a directed graph. And by the way, depth first search can be done in both directed graphs and undirected graphs. They're really, the difference is very, very little, but I'm going to explain this to you and you can see what goes on. So the way this happens is for depth first search to take place, typically by the way, the reason we're going to understand depth first search in this complicated way is that it helps, it facilitates solving many different kinds of problems. And you'll see that once you kind of figure out how to solve it in this manner, it'll lots of other problems will be just a cakewalk for you. Okay, so that's the reason why we want to pay attention to this and make sure we understand it. So the way this works is depth first search always starts from a single vertex. And you, as a user, you have to specify what that vertex is. Of course, if you don't specify, you can go and pick a random vertex and start off your depth first search. So you can either assume that it's given to you as a starting point, or you can assume that it's you randomly pick one, or you let's say you always pick vertex number 1. Now the way this goes is every vertex we're going to go and visit them in some strange order. In this case, what's called as the depth first search order. And before the vertex is visited, we are going to color the node as and say that it's white in color. If we have visited it once, we're going to color it gray, and once we have finished with it, we're going to color it black in color. So vertices will always go from being white colored vertices to gray colored to black colored vertices. And you'll see how this progression will assist us in understanding depth first search in a clear manner. So because to start with, all the vertices are white in color, you haven't visited anything. Let's say you start at this vertex U. The moment you start there, the first thing you do is you color it gray. So the moment you visit it once, you color it gray. And we also provided what's called as a depth first search number. In this case, we are going to give it the number 1. That number is written on this vertex itself. So every vertex, when you first see it, it'll be given a number. And then when you've finished with it, it'll be given a second number. It's called the finish time, and you'll see why all of this makes sense. So when we start with, we give this vertex number 1, and then we look at the remember the adjacency list that we talked about in the previous slide, not the previous slide, this slide here. We're going to use, remember, it's actually the same graph that we're going to use for the depth first search. This is our adjacency list. Vertex 1 is connected to 2 and 4, 2 and 4. Vertex 2 is only connected to 5. Vertex 3 is only connected to 6 and 5. Vertex 4 is only connected to 2. That's this edge here. Vertex 5 is connected to 4. And vertex 6 is only connected to itself. That's 6 to 6. So this is our adjacency list. We're going to use this representation for our depth first search. And as I said, we're going to start off with vertex number 1, and then we're going to systematically go through the adjacency list for vertex number 1 and go and visit all the edges that are adjacent to vertex number 1. Our goal is going to be, we're going to try and visit all the vertices and all the edges that are adjacent to them. So right now we haven't visited anything. All we have done is to see vertex U for the first time, and we've given it the depth first search number of 1. And when we look at the first edge, it turns out that the first edge goes from 1 to 2. So that following that edge lands us in a vertex that used to be white in color. So we immediately label it as 2, and we color it as a gray node. Remember, when something is colored gray, it means it's already been visited for the first time, but has not yet been completely processed. So gray means that it's under processing. Now, the way depth first search works is, instead of traversing all the edges from 1, when we get from 1 to 2, we pick one of the edges that lead out of 2. In this case, there's only one edge that leads out of 2, and it goes to 3. And we're going to pick that edge and do the traversal. The next time around, we're going to pick the only edge that leads out of this vertex 3, and we're going to go to 4. So remember, the vertices will end up getting numbered 1, 2, 3, 4, because that's the order in which we saw these vertices. Now, when I get to 4, I will look at all the edges. Turns out that there's only one edge that we have to look at. And this leads to a vertex that's already been seen before. It's already gray in color, so we're not going to do anything with this edge. We're just going to mark it as visited and move on. And so this edge turns out to be an edge that we are not going to be interested in, because it leads to a vertex that we have visited before. And so we're going to back off and continue doing the search from here. By the way, the edge that leads you to the vertex for the first time is going to be, it's made dark colored edge here. It's made thick so that, because that's an edge we are going to be interested in later on. So these dark edges are edges that take you from 1 to 2 for the first time, from 2 to 3 for the first time, and from 3 to 4 for the first time. Now, this edge from 4 to 2 is an edge that didn't take you there for the first time, and so therefore we're not going to be interested in it. In fact, we're going to make this edge as a dotted edge, and if you look closely here, you'll see that this edge here is a dotted edge, and so we're going to treat it somewhat differently. In fact, it's not going to become a fat edge like these other guys here. So it turns out that from vertex number 4, we don't have any other edges to worry about. There are no other edges that are leading out. There was only one, and we've taken care of it. We visited it. So at this point, we're going to say that we are done with vertex number 4. And so we will give it a finish time. And the finish time, because 4 has already been used up, the finish time is going to be 5. So what this says is this vertex was visited for the first time at time 4, and at time 5, we were done with it. We don't have anything more to do here. And so at this point, you're going to go back to wherever you first arrived at vertex number 4. And we already know that vertex number 4 was arrived at for the first time from this guy here. So we're going to go back here, and we're going to see if there are other edges to explore from here. And we see that there are no other edges leading out. And so we're done with this. We'll give it a finish time of 6, and we'll go back to where we came from over here at 3. In this case, that turns out to be vertex number 2. And so we go back here, and we see if there are any other edges to take care of. There are no other edges that are leading out. So this becomes vertex number 7. And we return to wherever we got here for the first time. That would be vertex number 1. And here we check if there are other edges to take care of. And it turns out that there is a single edge to take care of, but it leads to a vertex that's either gray or black in color. So we're going to ignore this particular edge. Once we do that, we know that we have nothing more to do here because all the edges leading out of 1 have been taken care of. So we're going to color this vertex as black, give it the number 8, and move forward at this point. So our depth first search currently has managed to visit 4 vertices. In this case, it's managed to reach 1, 2, 3, and 4. and we are done with them because they're colored black. There are no more edges leading out of them. And so at this point, depth first search would stop, and it would ask if there are new vertices to be taken care of, new unvisited vertices to be taken care of. And you'll see that, yes, there are 2 vertices that have been unvisited. And so it'll randomly pick one of them and continue its depth first search. So in this case, it'll start by picking this guy. Because we've already gone up to 8, this is going to have a number 9 as the time point when it got visited for the first time. And so here we're going to look at all the edges going out. It turns out this edge leads to a vertex that's already been seen before, so nothing will happen. But this edge leads to a new vertex, so this guy will become number 10. And that's what you see over here. Vertex number Z is going to be labeled 10 because at time instant 10, it got visited for the first time. And we also see that 10 has an edge leading out, but it leads to a vertex that's also gray in color, which means that this edge will not lead to a new vertex. And therefore, we are going to be done with this vertex. And we're going to label the finish time as 11 and return to where we came here from. In this case, that would be this vertex. And since there are no other vertices, no other edges leading out, we're going to stop here and label this as 12 as the finish time. So at this point, we have visited all the vertices. They're all black in color. All of them have a start time and a finish time. And all the edges have also been visited and labeled as visited. And so at this point, depth first search can stop. So this depth first search allowed us to systematically go and visit all the vertices and all the edges in the graph. And that was the whole point of this exercise. Now, you should stop and ask, why do I bother with all of this? Why can't I just go and visit all the vertices in some other order? What you will see is that depth first search has some amazing properties which will help you to solve lots of really interesting problems. And slowly we'll get to those as we move forward. Are there any questions about depth first search in a directed graph?
Couldn't we start it at W instead of V?
Yeah, I did tell you that you can start at any vertex you want. It's a user-defined vertex that's a starting point. If you start at V, it'll give you a very different depth first search. The order of vertices that will get visited will be different. The numbers will be different, but it'll still be a valid depth first search. So depth first search depends on where you start and what is the layout of your adjacency list. If your adjacency list has a different order, then you will get very different order in which the vertices will get visited. Any other questions? Yes, Clement.
So in the case of, we have edge B, where it goes to like one of its ancestors, would that be like
Where there are no ancestors. There is no, what do you mean? So tell me.
I mean,
which number? Give me a number or a label. X to V, or what are you talking about?
Oh, I was talking about from X to V. Yeah.
Yeah. Okay. So you're right. It is an ancestor. What about it? What's the question?
Oh, I mean, would that be like a cycle in the graph?
Yeah, this graph does have cycles. So I never told you it's a tree. Remember, it's only in trees that you're not allowed to have cycles.
Oh,
okay. This graph is not a tree.
Okay.
Right?
Right.
So there'll be all sorts of things here. There can be cycles. There can be whatever you like. Okay. But the goal is, it shouldn't matter whether there are cycles. Remember, if there are no cycles, it's sort of easy to go and do depth first search. Mm-hmm. Because whatever path you follow, you're going to find new guys. It's only because you have cycles that you might end up visiting something over and over again if you're not careful, right?
Right.
So that's why depth first search is handled in a careful manner so that you don't go and visit vertices over and over again. You want to visit them, but you want to visit them only once. Now, in this case, it told you, I told you exactly what order in which the vertices got visited. And it turns out that this ordering becomes extremely important later on. Now, because this is a directed graph, it looks a little bit different. However, you'll see that these big fat edges have a direction. So this edge here goes from U to V, this goes from V to Y, this goes from Y to X, and then this goes from, over here goes from W to Z. Now, these big fat edges, if you just focus on those edges, it turns out that it's always a tree. In the sense that it will never form cycles. If it's only these other edges that could form cycles. But if you only focus on the big fat edges, you will see that they don't form cycles. So these big fat edges constitute what is called as a depth first search tree. It's a tree that results from applying depth first search. And that tree, it turns out, has some fabulous properties which will become useful to us later on. And whatever I said is true independent of whether you're talking about directed graphs or undirected graphs. There are some subtle differences, but we'll focus on this a little bit later. Are there any questions? Or was this too fast? All good here?
All good.
All good. Okay. So in some sense, depth first search is very easy. You keep following your edges as long as you can go. If from a point there are no other new vertices to explore, then you back off, back up, and you continue your search. That's what we did here. We started from vertex U, we went to V, we went to Y, we went to X, and then we couldn't go anymore, so we backed off and backed up all the way to U, and then restarted the search in this case. In a undirected graph, the way we restart may look very different from this example. Now, the order in which we visit these vertices is exactly what you see on the labels. So even though the labels to start with were U, V, W, X, Y, Z, the order in which these vertices were visited was different. This was 1, this was 2, this was 3, this was 4, this was 9, and this was 10. And that's the order in which the vertices got visited. So we know that something that's labeled 9 will be visited before something that's labeled 10. We know that something that's labeled 2 is always going to be visited before we visit a vertex labeled 4, and so on and so forth. So depth first search may be very simple in principle, but when we apply it, it turns out to be a lot more interesting, and we'll talk about that in a couple of minutes.
Professor Giri.
Yes, Adriana.
How would this work in a Hamilton circuit?
Yeah, that's too early to ask. We'll put that discussion to much later, because Hamiltonian circuit is what's called as a NP complete problem, and you're not ready for that yet.
Okay, got it.
Okay, yeah. But quickly to answer your question, Hamiltonian circuits must visit every vertex. Here, we are not interested in circles or cycles. We're only interested in traversing every vertex and every edge of the graph. Okay, that's our goal. All right, so I'm going to show you some pseudocode for depth first search, and what you'll see is that the way it's written, it applies perfectly well for both undirected and directed graphs. So let me show you the code. Here is, so we'll actually write it in two parts. And in fact, it'll be a recursive program. And the recursive call is going to be called DFS Visit. DFS stands for depth first search. And what this does is it initiates depth first search visit starting from vertex U. Okay, so that's the way you describe this particular function. And the way it starts is very simple. When DFS visit is initiated at vertex U, the first thing it does is it assumes that the vertex was never visited before, and it's going to do whatever it takes to go and visit that vertex. Remember, our goal for a traversal is to visit every vertex and visit every edge. So that's why over here, the first thing we do is we go and visit it. Now, what this means in practice is that when you visit a vertex, you could do whatever it is that you wish to do with that vertex. But a traversal helps you to traverse this in a systematic manner. What you do at each vertex is completely up to you. So the good thing is that you can take depth first search and adapt it for solving many other problems. Now, after you visit the vertex, remember, we are assuming that it was never visited before. So we are going to assume that it used to be white in color. So the first thing we do is we turn it gray in color to indicate that we have now seen it for the first time. We are also going to give it what is called as a depth first search number. The depth first search number is going to be stored in an array called D. So D of U is the notation we're going to use for indicating the depth first search number of a vertex. We are going to keep track of the number of steps. In this case, we're going to call that time. So the depth first search number is whatever is the current time. When we get started, the time is going to be initialized to 0. So therefore, the first vertex that you visit will get a depth first search number of 1. Then later it'll become 2, 3, 4, whatever. And then once you have visited the vertex, once you've colored it gray, and once you've given it a depth first search number, the next job is going to be to visit all the edges that lead out of this vertex. And so what we're going to do is to look at every vertex that's in the adjacency list of U, which is the same as saying all the vertices that are adjacent to this vertex, you go and do something. In particular, you're going to visit that edge and you're going to initiate what's called as depth first search starting from that vertex. But you only initiate the depth first search from that vertex if the color of that vertex at the other end of this edge is white in color. And so that's what we see here. We're going to do for every vertex V that's adjacent to this vertex U, we check whether it's white in color. If it is white in color, we just go in and make a recursive call for our depth first search visit, but starting from this vertex V. When we are done with this entire for loop, we would have visited every edge that you can use to go out of this vertex U. And at that point, we are done with everything we have to do at vertex U, and we're going to color it black, and we're going to give it a finish time, a finish number. And this finish time simply increments the time and puts it and stores it in an array called F. So D of U gives you the depth first search number. That's the time at which it was visited for the first time. And F of U is the finish time. That's the time at which this vertex is finished, and you're never going to visit it again. So that's your basic depth first search starting from any vertex. But it's important to understand here that it's a recursive program, and it invokes itself, but from the new vertices that it encounters in the process. Now, of course, this is a recursive call. A recursive call needs to be called from somewhere, the main program, and that's what I'm going to show you over here. So the main program, or the calling program, is called depth first search. This is called depth first search visit. This is called depth first search. The way depth first search works is we're going to look at all the vertices. We're going to color all the vertices as white. That's how we initialize it. I'm going to explain step number 3 a little bit later. We're going to initialize time to 0. And then from each vertex, we're going to make this recursive call that says, if the color of that vertex is white, then initiate depth first search from that vertex. So what this also means is that if you want to initialize depth first search from a specific vertex, then you do all these initializations and simply call this depth first search visit from you for the first time. And then after that, it will take care of itself because it has these recursive calls that will find neighbors and initiate depth first search from there, and so on and so forth. So this is the complete depth first search program. And it will work for both directed graphs as well as undirected graphs. And it runs in time big O of m plus n that you see up here on the right-hand top, where m is the number of edges and n is the number of vertices. So it's a very efficient algorithm. It's linear in the number of vertices and edges. And in the process, we do some very, very interesting and useful things. We set up what is called as depth first search number. We set up what's called as the finish time. And we also, we can figure out a bunch of other things, and you will understand that in a few minutes. Are there any questions before I move on? Do you want me to go over any of this again? Okay, hearing no questions, let me move on. Now, what we're going to do next is to try and understand what this piece of code helped us to do. Why is this really, really useful? And how is it going to help us to solve other problems? That's what we're going to look at next. So in order to do that, we're going to try and look at something called the depth first search tree. Now, let me go back a couple steps here to the previous slide. If you remember, we did this example with a directed graph, and we did depth first search there. Yeah, this one here. Oops, sorry. Oh, come on. Okay, so we did depth first search with this graph here. Now, the big fat edges here constitute what is called as the depth first search tree. And the reason it's a tree is because there are no cycles. If there were a cycle, then you would end up visiting a vertex for the second time, which is never going to happen, because the moment you see a vertex is gray in color, you're not going to initiate depth first search one more time from that vertex. You only do it once, and that's when it's white in color. That's why you never end up visiting same vertex more than once, and that's why these big fat edges never form cycles for you. Did that make sense to anyone?
Yeah.
Yep.
Okay, so so the depth first search and gives rise to a depth first search tree, which of course, because it's a tree, doesn't have cycles. Now that tree will become very useful as we move forward, and I'm going to show you what that looks like. If you look at the example that we worked out, what you'll see is that every edge in this graph goes from one vertex to another, and when you go when you visit vertex from vertex, if you visit V for the first time, we're going to call U as the parent of V, and if it's the parent of V, we're going to say pi of V is U, which means the parent of V is U. Now, pi is the notation we're going to use for the parent pointer. So this says store in that vertex a parent pointer, and that parent pointer is to the vertex U. And because you visited vertex V for the first time from U, we're going to call U as the parent of V. Now, if you only look at these edges going from a parent to a child, this gives rise to a depth first search tree. All the big fat edges that we saw in our example, those are all edges that we use to visit new vertices for the first time. And so therefore those edges go from a parent to a child. Clement?
Oh, I was gonna ask, so is that why, like, at the beginning in the DFS, the original DFS function, we set pi u to nil?
Yes,
Because there's no
exactly,
parent.
because the start node has no parent pointer.
Okay. All right,
So that vertex is simply not going to have a parent. Everything else will have a parent, which will tell you where you visited, from where you visited for the first time. And that pointer also helps you when you finish with depth first search from a vertex, you always go back to the parent. Is that clear?
that's clear.
Okay. Now, here is a property that's going to be very, very useful. This one says, if I gave you an undirected graph instead of a directed graph, and if the graph is already connected, then the depth first search tree will go and connect everything. So let me say that one more time. If the graph is already connected, then the depth first search tree will connect all the vertices. And this is an important property because now we can use this to figure out some properties related to connectivity.
Professor,
Yeah.
when you say connected, you mean starting at one vertex, there's a path to every other vertex?
Exactly. Exactly. So yeah, I guess we never defined connectivity. We're going to call a undirected graph as connected. We're going to call a graph connected if we can get from anywhere to anywhere. Now, that's very easy to think of in an undirected graph where there are no directions. But if you have a directed graph, you're only allowed to follow edges in the direction of the edge. There, this concept of connectivity is a little bit strange. We'll talk about that. I'm going to delay that conversation to a little bit later. So what this tells you is, if I have a undirected graph, and if it's connected, then your depth first search, it doesn't matter where you start, but when it finishes the depth first search, it's going to go and visit every vertex and every edge in the graph. And that's a given. And the reason is quite simple. If you start at a vertex, eventually you'll get to all its neighbors. If you get to all its neighbors, you will eventually get to all its neighbors, and so on and so forth. So if the graph is connected, then you will get from any vertex to any other vertex because they're all connected. So therefore, your depth first search will take care of traversing every vertex in the graph. And because when you get to a vertex, you look at its adjacency list and you look at all the edges that lead out of it, you can also be sure that if the graph is connected, you will end up traversing not only all the vertices, you will also end up traversing all the edges in the graph.
So in the example we had, you couldn't go to X,
Correct.
was it? Because
Correct.
it was
So
directed, right?
Because it's directed. So directed ones are complicated because connectivity itself is a strange concept there, and you're absolutely right. So let me see if I can get to that example. Yeah, it's this was the example. And what you see here is that you didn't get one tree. In fact, it got broken up. So all you could do was to visit these 4 vertices, and then you had to restart the process in order to visit these 2 guys. And that's because this graph, this was a directed graph and it was not connected. So because of that, you couldn't visit everything in one shot, and you had to restart the depth first search in order to make it happen. When you first started it from U, all it managed to reach was all these guys. In fact, from here, you can't get to this side, right? Because there are no edges going in the other direction. And so that's why you end up with a tree in 2 pieces. It's also called a forest, by the way.
Knowing it means eating simply, growing pumpkins and cassava, boiling or drinking water, hanging clothes to dry.
Hold on a second.
At first primitive to us,
Karne,
village life has become more
stop
familiar
that.
and attractive with each passing day.
Hit pause.
On the island, 5 miles wide, 9 miles long, Fijians walk everywhere, up into the hills to work their plantations, along the roads to young.
Sorry about that. Okay, so what I was saying was that in this case, the reason depth first search couldn't visit everything was because it was not connected in the sense of a directed graph. For instance, there is no way to get from vertex U to vertex Z, and so therefore, you wouldn't get one depth first search tree. Does that make sense?
Yeah.
Okay. All right. So so it turns out that, as I said, it's possible to. This is a very important property, that if you have an undirected graph and if it's connected, then your depth first search will end up visiting the entire graph, will end up traversing the entire graph. Now, here is one more nice property. By the way, by the same token, you can also claim the complement or the contrapositive of the statement that says that if the graph is not connected, then remember those big fat edges that we had, those big fat edges will not give us a single tree. Instead, they will give us multiple pieces. And if it's in multiple pieces, it's not called a DFS tree, it's called a DFS forest because there are multiple trees. Is that clear? Now, for the directed case, there is something called a strongly connected. If you can get from every vertex to every other vertex, then you'll end up with just one tree. If that's not so, then it's not always that you'll end up with one tree. You may end up with broken pieces, depending on where you start. Today we'll focus on undirected graphs. For directed, it's a little more complicated. So let me try and explain some important properties of undirected case. I will right. So I am going to skip this slide and come back to it later. Now, I didn't define connectivity before. I should have had this slide a little bit earlier. It says that an undirected graph is connected if there exists a path between every pair of vertices. If you use the properties that we mentioned before, if you do depth first search on an undirected graph, you'll just get one big depth first search tree. So one way to check if a graph is connected is to simply run depth first search the way it was described on a previous slide. And if you just get one depth first search tree, then what you have is a connected graph. If the graph is not connected, then it surely has a bunch of connected components. A connected component is a connected subgraph that is maximal in the sense that you can't add anything more and still keep it connected. These connected components each requires a separate depth first search. And that's the good thing about the way we've written depth first search, and I'll show you that in a second. So if you want all the connected components of the graph, then all you have to do is to run depth first search, and you can figure this out. So let me explain what that means. If you go back to this code here, remember that, well, let me show you the whole thing. Yeah. Okay, so this is your DFS code. If your graph is connected to start with, and if you start at this main program from any vertex, it will go and complete the depth first search and end up visiting all the vertices and all the edges by the time it finishes. And remember, it's all recursive, so it kind of takes care of itself of doing the of following up and visiting all the vertices. So all I have to do is, if it's a connected graph, I can pick any vertex. As long as it's undirected, I can pick any vertex, set off the depth first search, and it will go and visit everything in that graph. Now, how would you know that it did not visit everything in the graph? Can you tell me? Anyone?
If one of the vertices is white.
That's right. So if you end up with a vertex that's still white in color, then you know that there was a disconnected piece. Now, I also defined for you what are called as connected components. And connected components are, if you have a graph that's disconnected, each of the pieces is called a connected component. Now, can I use this code to figure out the connected components of the graph?
Didn't you say that we could?
I said you could, but how do I do it? How do I modify the code here to figure out my connected components? Anyone?
Is there a way to figure out how many components there are to begin with, or?
That's what I want to find out. I don't know to start with. I'm just given a graph. I have no idea whether it's connected or not, or how many pieces there are. I want to figure all of that out.
You want to figure out how many components there are?
And also each of the components. But yeah, let's start with how many components.
For how many components?
Yes.
In DFS of G, in
Yes.
the for loop of 5, you can do a
Yes.
counter. You can start off at 0, and then inside the for loop, increment it to 1.
Very good. Very good. So right over here, remember, if the graph is connected, I can start from anywhere, and by the time it finishes the depth first search, I should have all the vertices should be black in color. So I won't be able to restart it again. But if the graph is not connected, then somewhere down the line, you're going to have to revisit statement number 7. So every time I get to statement number 7, over here in the main program, I know I am going to a new connected component. Does that make sense?
Yes.
So all I have to do is to put in a counter right there between 6 and 7 and say count equals count plus 1. And that'll tell me my number of connected components. Fine? Can you handle that? Now, how do I figure out the actual components? How do I figure out which vertices are part of which component?
Which vertices are inside which component?
Yeah.
So
I'd like to know which set of vertices are all part of the same component. I'd like to know which set of vertices are not part of the same component. Is there a way for me to handle this?
Can't you add a counter after 10?
Why 10? Where'd you get 10 from?
Oh, not line 10, but line, yeah, after before line 10, add a counter. To see how many
So let me help you a little bit. Let's give each of the components a number. Okay, let's call one of them component 1. Let's call one of them component 2, then 3, then 4, then 5. That way we'll also get a count of the components as well. How can I find all the vertices in component 1, all the vertices in component 2? How do I modify this code?
In line 11, instead of coloring black, you color it the number.
That's right. So for that, I'd have to pass the component number. So the first time I call it, I'm going to pass it 1 to say, hey, all of these are going to be part of component number 1. When it comes back, I'll increment that count, and whatever vertex I'm going to restart with this whole thing with, I'm going to pass it number 2. So all the vertices that I visit there will be part of component number 2. Does that make sense? So I will give this an extra parameter called component number. I will initialize component number to 1, and I'll initialize it to 0, and just before calling this, I'll increment it and pass it to DFS Visit. But when DFS Visit is called when it's called recursively from within here, I will give it the same component number so that all the recursive calls are all part of the same component. Only when it returns to the main program will I increment the component number. Does that make sense?
Can you repeat the last part?
Right. So we're going to manage component numbers from the main program, not from the recursive program. From the main program, I'm going to initialize component number to 1, so that the first time I call, I invoke statement number 7, it's going to pass as parameter to this procedure the component number 1. All the vertices that are visited here will be called component number 1. When you make a recursive call, it'll stay as component number 1, and so on and so forth until it returns back here. When it returns back here, it's going to increment the component number to 2. And now any new depth first search visit that you invoke will get component number 2. So all the vertices that are part of that component will get labeled as number 2. And so on and so forth. So we have to add an extra statement here that says component number of u is whatever it is you pass as parameter, the component number. So we'll create an extra parameter here called component number. That component number will be passed here, and the component number of u will be whatever is the number that's passed to it. And component number will get incremented here so that the next time you reinitiate depth first search from a new component, all the vertices there will get a new component number. So this way I can label all the vertices with their component numbers, and all the vertices within the same component will get the same label. Did that make sense?
Yes.
yes.
Okay. Or was that too much for you? This was okay, right?
Yeah, it was okay.
Yeah. So so as long as you're able to handle this code, you can modify it to do all sorts of interesting things. And this is the easiest of the interesting things that we want to do. We can figure out whether the graph is connected. We can figure out if it's not connected, how many connected components there are. if it's not connected, we can figure out all the vertices in each of the connected components. Is that clear?
Yes.
Okay, so once again, let me just to make sure that everyone got this. How do I figure out if the graph is connected?
You initialize a number at the beginning.
All I want to know is the graph connected or not? I don't want to know anything about component numbers.
Oh,
Is that a simple solution? Go ahead, Clement.
Well, how do we confirm that the graph is connected?
Yes.
We'd have to check if there's a path between every pair of vertices, but how?
Oh, Clement, you were not listening.
Oh, wait. Okay, hold on.
What did I tell you? What is this property here? What did it say here? What does it say here?
For connected undirected graph, these edges form a tree called the DFS tree.
Right. So what is the implication of that?
All right. So would every edge have to exist within
the graph is connected? What happens? What should you see here when you invoke this program?
Wait a second. So essentially, it's that if it's a depth first search tree, that means that the first node is the parent node for all the other nodes, right?
Not the parent node, but yeah, it's the starting point, and you will end up visiting every vertex, and all that will happen in here, not there.
Okay.
So, how do I test whether it's connected? You didn't tell me that. Yes, Lazaro.
Yeah, if it is connected, then after the first run, they should all be black. That means in the pi array, it should all be black.
The count should just be one.
I told you something even simpler here. What was that? Remember, statement number 7. That's the important statement. If you ever get to that statement more than once, what does it tell you?
There's 2 components. There was a node that was white.
That's the key. So if you only call it once from here, it's connected. Because everything got colored, there is no more white vertices to left to restart depth first search visit, right?
Mm-hmm.
Right.
So if I never get to this statement more than once, then I have a connected graph.
But without a counter, would what I said?
You don't even need a counter. You can just have a Boolean flag, right?
Oh, okay.
Right. Yeah.
But wait, but still, since if it is connected, it will only run once. That pi array, it would be completely filled, correct?
Yes.
Yes. Okay. Okay.
Well, the first guy will have a nil pointer because it has no parent. But yeah, you would have another thing you could do is when you visit a vertex, you can keep a count. And if when you get here, the number of vertices you visited is already n, and you're done.
Sure. Okay.
So there are many ways to do this, but this is important that you will never reinitiate depth first search from here, from statement number 7. That's important. Okay.
Yeah.
There are no other white vertices. They've all been turned colored black and they've been processed. Remember, black means they've been processed. Gray means that they are still in processing, and white means they've never been looked at. Okay. So you use the colors to figure out whether you have to restart depth first search from over here. If you never have to restart, then it's already connected. And all you have to do is to modify this code here in a little bit. And there are, we talked about 2 or 3 different ways to do this, right? You could use a counter where you count the number of connected components. And if that number is only 1, then you know it's all connected. You could set up a counter in here that counts the number of vertices that get visited. And if after the first time you call DFS visit, if it ends up visiting all the vertices, then of course it's connected. Or you can count how many times you invoke DFS visit from statement number 7. If you only do it once, then number of connected components is 1. If you do it 3 times, the number of connected components is 3, and so on and so forth. Is that clear?
Yes, that's clear.
Okay, so depth first search as defined here looks complicated, but anyway, it's just a piece of code. You just take this and stick it in your program. But it can help you to solve many interesting problems. And so far, I've only told you 1. Well, actually, I've told you 2 or 3 because it tells you whether it's connected. It tells you how many connected components there are. It tells you which are the various connected components, right?
Right.
Okay, any questions so far? I see a couple of questions in the chat. Let me see if I... Okay, no problem. Yeah. All right.
Oh yeah, oh yeah.
Okay, let's move on to the next. So we're going to look at some other interesting applications of graph traversal. So the first one we already talked about. We can check for connectivity of undirected graphs, right? And it says what I said earlier. If we return to statement number 7, then the number of times you return to it is the number of connected components. If you never return to it, then then the graph is connected. Is that clear?
Yeah.
Yep.
Okay. So that's what I just said. The vertices and edges visited between returning to statement 7, all of those form one connected component. So in between your return to statement number 7, everything you visit is one connected component. Okay. Now, I'm going to tell you that depth first search can be used to check whether your graph has cycles. Now, I'd like you to help me figure this out.
Now?
How can I modify this code here to check if the graph has cycles?
If
it reaches the first node once.
First node. Why first node?
Because a cycle is the start point is the end point.
Well, the cycle may not include the first guy. We don't know where we're going to start.
Sorry, didn't interrupt. But,
yes, Harpreet.
But for this problem, wouldn't you have to necessarily check in terms of cycles, like if if the node you're going to visit is already colored black, and then wouldn't that constitute that like constitute a cycle since it's already been visited once?
Sure. So tell me how to modify this code to check for cycles. You're right.
That I am very confused on because I'm only a first year, so I have very little.
That's okay. Yeah.
So I'm guessing if you can during line 6 where you're gonna visit, when you're gonna visit, you can add you can have like a Boolean flag to check if it's cyclic, and then when you're visiting, like the part where you're checking if v is not equal to, sorry, pi of u, then you can check if the color of your vertex is black already, and then you can set the flag to true.
But it
I
is being
guess.
checked.
Oh.
It is being checked.
Mm. But
We're
then
checking if it's white. So what would you like me to check?
Sorry. Like, oh, sorry. When you're gonna visit edge UV, I assume, like below that, I'm guessing you can kind of add like an if statement to check if the color of U is already black, I guess, because since you already defined it once.
Why couldn't it be gray?
Oh.
Could it be gray? You're on the right track, by the way. Keep going.
Sorry, I just kind of forgot a little. So gray means the edge. Sorry, the edge is visited or the vertex is visited, because I'm kind of confused on
gray. So colors are attributed to vertices.
Okay.
A white vertex means you've never seen it before.
Okay.
Gray means you've seen it before, but you haven't processed all the edges leading out of it.
Mm-hmm.
And black means you've already processed it. You've looked at all the edges leading out of it. There's nothing more. You're never going to see it again.
Okay, then I assume it could be gray as well, because since although you've already seen the vertex, you haven't seen all the edges.
Okay. Very good. Okay. So how do I modify the code here to take care of what you just said?
Well, then I'm assuming that when you are going to like when you're checking each vertex in the adjacency list, I'm guessing like you
which statement? Which statement is that?
Sorry, line 5 in the for each statement for each v.
Okay. Yeah.
In the adjacency, I'm guessing you can kind of do like a statement when you are going like I believe you have to set it before to where you have to check if the color of U is either.
Well, you're going back to color of U. It's actually color of V. But anyways, yeah.
I'm sorry about that. I kind of got mixed up.
That's fine. Yeah. So let me explain this a little bit. But is there anyone else who wants to jump in and give me an answer? But that was a good effort, Harpreet.
Yeah, I was just going to basically say the same thing he said before line 8. Check if the color of V is either gray, because you know we're processing that vertex, or if it's black, we've already seen it. And if it is, then we know there's a cycle.
That's very good. Instead, I'm just going to put it here as else. If color of V is white, then it's leading to a vertex you've never seen before. So you're going to reinitiate depth first search from there recursively. Otherwise, if it's not white, then it's either gray or black, right?
True.
So I put in an else here. And if I say in the else part, what do I say? Are you now sure there's a cycle? So look at what has happened. You started somewhere, you colored it gray, and then you followed edges along the way. And as you visited new vertices, you turned them gray in color. And then you found an edge that leads back to a gray colored vertex. That means that you now have a cycle that's going back. Does that make sense? So the moment you find an edge leading to a gray colored vertex or black, you know that there's a cycle. Now, what I just said only works for undirected graphs. For directed, it's actually a little more complicated. Any questions about this? Did that make sense?
Mm-hmm.
So I haven't really shown you the entire code, but I'm just explaining this to you, and I'm hoping that you are following me. I am going to remember in statement number 8, right? In statement number 8, I'm checking if, so remember, I'm doing depth first search from vertex U. I'm looking at all the edges leading out of it. In particular, I look at the edge from U to V. If V is white in color, then it's a new vertex. I've never seen it before, so I'm perfectly free to go and make a recursive call for depth first search visit from that new vertex. However, If it's not white in color, then it's a vertex that I've seen before. And so therefore it's either gray or black. If I have an edge that leads to a vertex that's colored gray or black, then it means that you're now coming back to that vertex. If you ever come back to a vertex, it must be because it's a cycle. If remember the definition, we said that a graph is a tree if there are no cycles, right? You remember this?
Yeah.
So therefore, if you only have a tree, you'll only see every time you visit a new vertex, it's going to be white in color because you're never going to go back because there are no cycles. So therefore, in a tree, if you do depth first search, you will only encounter new white vertices. But if there is a cycle, then you are eventually going to have to go back to a vertex you've seen before, and that's your indication that a cycle has been noticed. And that's when you stop and say, okay, this graph has cycles. So going back to the applications, what I just said was you can check for cycles by simply modifying depth first search in a very simple way. At statement number 8, where you check whether the vertex V is white in color, you stick an else clause that says if it's not white in color, then it's a cycle. So then this graph has at least one cycle and we're done. So if there is a cycle, then this graph is not a tree. And really that's what this question is asking you to check. Is that clear? So restating what I just said, the statement 8 checks whether the vertex is white in color. If that condition fails, then a cycle is detected and you can stop. Everyone okay with this?
Yeah.
So any edge that passes the condition in statement 8 does not form a cycle and it's part of the tree. So that's why the big fat edges are marked right in that if statement of statement number 8, and there you only get tree edges. But the moment you see something that's not part of that if statement, if it fails there, it's an edge that leads back and so therefore forms a cycle. Okay. So this is the most efficient way to test if a graph has cycles. All you do is run depth first search and modify one statement there, and you can report whether the graph has cycles or not. Everyone okay with this?
Yes.
Okay. Now, it turns out that you cannot use this to count the number of cycles or things like this, but you have to be a little bit careful here. There are some fairly complex problems that you might think you can solve with this, but it doesn't necessarily work. Cycles are very, very tricky, but what I just described to you is one of the best ways to check for cycles in a undirected graph. If you have a directed graph, it's a little bit trickier, and we can discuss that separately a little bit later. Any questions? So I should say a little bit about directed graphs. If you run depth first search on a directed graph, then you could have two different things. The color is, if the color is white, you know that it leads to a vertex that you've never seen before. And so that's a new vertex, and therefore you can start, you can recursively call depth first search from there. If the color is gray, then you know for sure that this is a what's called as a back edge, and it forms a cycle. However, if the color is black in a directed case, then it's not a cycle, and that's tricky. In fact, the example comes over here. You'll see that when you were here, by the way, let's see here. This graph does have cycles, and you'll see how that shows up. The first edge you pick is this guy. The second edge you pick is this guy. The third edge you pick is this guy. But the fourth edge you look at leads to a vertex that goes from here to a gray vertex, and this forms a cycle. V, Y, and X forms a cycle. Okay, but you'll see that there is when later on, when you were at vertex W, you went to this vertex and everything was good, but then you also saw this edge. Now this edge led to a black vertex, and this did not form a cycle. So in a directed graph, if the edge leads to a gray vertex, it's a cycle. If the edge leads to a black vertex, it's not a cycle. So you have to be a little bit more careful in the directed case. But this idea of using depth first search, using colors, turns out to be a powerful way to check for cycles. Yes, Adriana.
Wouldn't if it's a directive graph, wouldn't like it consider itself like two components? Like in this case, because like
yeah, in this case there are two. Well,
it would consider itself a two components, even though it's kind of a connected graph, right?
Yeah, but counting number of components is a bad idea in directed graphs. It's actually a lot more complicated than what you just pointed out, because the number of components can be different depending on where you start the search. So I don't want to get into that. Let's stick to counting number of connected components if we only have undirected graphs. Otherwise, it's a little trickier. Okay.
Okay.
I can show you examples where, depending on where you start, you get either one component or more. Only in the directed case. Undirected ones are straightforward, and whatever I said will make a lot of sense. Should make a lot of sense. So back to this, we know two important problems we can solve, one related to connectivity and one related to cycles. We can solve 2 or 3 different problems related to connectivity, and we can solve an important problem related to cycles. We can check if there are cycles, and in fact, there is one more thing that we can check, and I think that's on the next slide, if I'm not mistaken. Any questions so far? Okay, so here is one more. We know that an undirected graph is connected if every vertex is reachable from every other vertex. A connected component is, well, so this tells you how to build all the connected components, and we already discussed this, so I'm going to skip this. Computing connected components, it tells you exactly how to do it, so I will let you read this later on. I want to move on to one more. Oh, I'm talking. Yeah, I don't want to discuss this weak and strong for now. Let's move forward with this. I think the rest have to do with breadth first search, but perhaps we'll do this. Breadth first search turns out to be very simple. You start from a vertex, and instead of following it all the way until you can't go anymore, you go from a start vertex to all its neighbors. From those neighbors, you go to all their neighbors, and so on and so forth. This is what's called as breadth first search. And breadth first search turns out to be quite useful, and the code is given here. you will see lots of parallels in terms of what we did, but there are some fundamental differences in what you do with breadth first search. And I'll try and explain that very quickly. Probably take another couple minutes to explain this. Oops, what happened here? Oh, something happened. Okay.
So let's do this.
Okay. So this is the pseudocode for breadth first search. Breadth first search achieves more or less the same things as depth first search in the sense that it visits every vertex and every edge. It also follows the same rules. When you start a vertex for the first time, it's colored white. When you visit it for the first time, it's colored gray. When you're done with it, it's colored black. But the way things are numbered is called breadth first search numbering. This is very different. The first vertex is labeled 0. All its neighbors are labeled 1. All their neighbors are labeled 2, and so on and so forth. And they have very different properties, and perhaps we'll talk about this the next time we have a chance. What I'm going to do is to, for this Saturday, when we have your mock competition, I'm going to give you a problem that's somewhat related to connectivity. And my goal is for you guys to pick up the depth first search code, program it, put it in, make sure that it works, and figure out how to apply it to the problem that I assign you for this Saturday. But I'm going to stop here for this lecture. If you have any questions, I'm happy to answer. You guys want to turn on your videos so that I can quick look at you and stop the session?
Sure, 1 second.
Any questions?
I have a quick question, Professor.
Yeah.
Like in line, I think it's 9. Like probably talking about NQ and DQ. What exactly are you doing there?
Yeah, NQ and DQ are what are called as queue operations.
Okay.
You are familiar with a queue. So NQ puts a new item at the end of the queue, and DQ pulls out whatever is at the start of the queue.
Okay. Thank you very much.
So it turns out that breadth first search uses a data structure that you're all familiar with called the queue.
Mhm.
And you can use this to implement breadth first search. Now, this is what is really, really nice about the way both the pseudocodes are written. Depth first search uses stacks, whereas breadth first search uses queues. And in fact, if you simply replace the stack with a queue, you'll get the other kind of search. And that's what is nice about the way this stuff is written. With some minor changes, what you need to remember going home is breadth first search uses queues, depth first search uses stacks. And remember, the depth first search code was written using recursion, and recursion uses an implicit stack. We never used an explicit stack. Whereas in the breadth first search, this is not written as a recursive program, and so we have to explicitly use a queue. So what we do is for every vertex, we look at all its neighbors and put them on a queue. Then every time we visit a vertex, we take all its new neighbors and put them at the back of the queue. And then each time around, you pull out the first guy from the queue and process it. And as soon as it's processed, you finish with it, you color it black, and you move on. So as I said, the only difference is that here you use a queue, there you use a stack. So if I were to simply replace NQ and DQ with a stack, I will get depth first search. Is that clear? So that's pretty magical. It's really useful for you to think about this and understand this because it has really, really special properties. Any other questions? If not, let's stop here and I'll set up a mock competition for Saturday at noon. It'll run for 5 hours. I'll try to keep the problems somewhat simple and related to graphs. Is that good? And I'll try and keep it to just depth first search, at least for this week. Graphs, it's a big topic. So each week we'll pick up, the next time we'll talk about minimum spanning trees, then we'll talk about shortest path, then we'll talk about all pair shortest path, and then we'll talk about network flow. So we have at least 4 weeks of just graphs and graphs and graphs. And if this is something that you enjoy and you want to learn, please come by.
Thank you very much, Professor Giri.
Okay.
Thank you, Professor.
Okay,
Thank you, Professor.
Take care, guys.
You too.
Stay safe.
Professor. Yeah, if you can send me the link and also the slides so I can share it.
Okay, good. Yeah, I can do both. Yeah.
All right.
All
Thank you
right,
very much.
And also,
See you
quick
next
question.
Yes, sir, please.
I'm not an FIU student, but am I still allowed to participate in the contest? Like the mock contest? Okay, thank you.
Yeah, you're welcome to join us. I don't care. All right. Any other questions? All good? Let's stop this. Good night. Yeah.
Good night.